Hello my dear students, in this lecture we will see principal stresses and maximum shear stress. As well as we will see the plane on which principal stresses are acting and the plane on which maximum shear stress is acting. Now, firstly we will start with principal stresses. Now, principal stresses means maximum and minimum stresses in the component. Maximum and minimum normal stresses in the component are called principal stresses. And the maximum normal stress, whatever may be the maximum normal stress sigma max, is called sigma 1. For 2D loading it is called sigma 1, and it is a major principal stress. It is a major principal stress, right? And the minimum normal stress in the loading for 2D loading, it is called sigma 2, and it is a minor principal stress. Now, these principal stresses are used in design. These principal stresses are used for design or used in design calculations, right? Now, principal stresses are used for the design, and minimum and maximum normal stresses are called principal stresses. Now, for loading, let us say consider for this loading, we have already seen that for such type of 2D loading, that is sigma x, sigma x, sigma y, and shear stress on the element tau xy, shear stress on the element tau xy, shear stress on the element tau xy. For such type of loading, if I consider any inclined plane at angle theta, the inclination of inclined plane is with respect to vertical in anti-clockwise direction. On this inclined plane there will be one normal stress, that is sigma theta, and there will be one parallel stress, that is shear stress tau theta, right? And already we have seen the formulas for this. What is sigma theta value? Sigma theta is nothing but sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta. This is the value of sigma theta, that is angle normal stress on any inclined plane at an angle theta with respect to vertical in anti-clockwise direction. Again, on the same inclined plane we can calculate shear stress tau theta, which is calculated as sigma x minus sigma y by 2 sin 2 theta minus tau xy cos 2 theta. This is how we can calculate normal and shear stresses on any inclined plane. Now, if I find, now as angle theta goes on changing, as theta changes, then value of sigma theta and tau theta also changes. As well as angle theta changes, can you imagine the sigma theta and tau theta also changes? Both will change, right? Now, and go on changing the value of theta, likewise. Let us say if I consider this theta, I will continuously go on changing the sigma theta, and on some plane you will find that this sigma theta is equal to sigma maximum, which is called sigma 1, major principal stress. And on some plane you will find this sigma theta as sigma minimum. This is called minor principal stress, right? Now, on some plane you will find this tau theta as tau maximum. This is called maximum shear stress plane. Now, our target is to find this sigma 1, sigma 2 and tau maximum, because for loading or for design calculation, always we have to calculate the maximum stresses acting on the element, and we have to consider the maximum stresses for the design of any component. Hence, we are calculating sigma max and sigma minimum. Now, firstly, we will calculate maximum normal stress acting on the component and minimum normal stress acting on the component, that is sigma 1 and sigma 2. Sigma 1 and sigma 2, that we will calculate first of all. Right. Now, while calculating, here I will write directly formulas, but don't worry for the derivation. In a graphical method, this is the analytical method, and in graphical method, while drawing more circle, I will explain the derivation also, how formulas are derived. This also I will explain in graphical method. As of now, for the sigma theta is equal to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta. Now, if this equation is maximized and minimized, then while maximizing you will get sigma 1 and while minimizing you will get sigma 2 as per mathematics. But here we are not learning mathematics, hence in graphical way I will derive these formulas. Now while maximizing you will get sigma 1, and this sigma 1 you will find that sigma x plus sigma y by 2 plus under root of sigma x minus sigma y by 2 whole square plus tau xy square. This you will find. And during minimization you will find sigma 2 as sigma x plus sigma y by 2 minus under root of sigma x minus sigma y by 2 whole square plus tau xy square, right? Simply I can write sigma 1 comma 2 is equal to sigma x plus sigma y by 2 plus or minus under root of sigma x minus sigma y by 2 whole square plus tau xy square. This is how simply I can write principal stresses. Sigma 1 is a major principal stress, and while calculating sigma 1 we have to put plus sign, and sigma 2 is a minor principal stress, and while calculating sigma 2 we have to put minus sign, right? Now here we have to understand some basics of principal stresses and principal planes. Now, the plane on which these principal stresses are acting are called principal planes. The planes on which these principal stresses are acting are called principal planes. The plane on which major principal stress is acting is called major principal plane. Is called major principal plane. Major principal plane. The plane on which major principal stress sigma 1 is acting is called major principal plane, and the plane on which minor principal stress that is sigma 2 is acting is called minor principal plane. Now see, understand here, as sigma is normal stress, that means this stress is perpendicular to the plane. This sigma is perpendicular to the plane, means for major principal plane, sigma 1 is perpendicular. For minor principal plane, sigma 2 is perpendicular, right? This is how we can call it. Now for 2D loading there are two principal planes. That is minor principal plane and major principal planes. For 2D loading there are two principal planes, that is minor principal plane and major principal plane. Now these two principal planes are separated by angle 90 degree. These two principal planes are separated by angle 90 degree, means angle between major principal plane and minor principal plane is 90 degree. This is very important. We will prove this. Don't worry about this. In graphical way, in graphical method, that is in more circle, we will prove this point. And very important point is that on both principal plane shear stress is zero. On both principal plane shear stress is zero. Shear stress, that is tau, shear stress tau is zero, means on major principal plane as well as on minor principal plane shear stress acting is zero. This is very important point. That means let us say, if this plane is major principal plane, if this is a major principal plane, then on this plane the normal stress is sigma 1 and the shear stress acting on this plane tau is 0, and angle between major principal plane and minor principal plane is 90 degree, means if this is a minor principal plane this angle becomes 90 degree, and if this will become minor principal plane. And again on minor principal plane the perpendicular stress is sigma 2 and shear stress acting on minor principal plane is also 0. That means the angle between major and minor principal plane is 90 degree, and on both plane shear stress is 0. This is very important point, and with the help of this point we can calculate an inclination of principal plane. That is, we know that tau theta on any inclined plane shear stress is sigma x minus sigma y by 2 sin 2 theta minus tau xy cos 2 theta. This is the formula to find shear stress on any inclined plane at an angle theta with respect to vertical in anti-clockwise direction. On principal plane, PP for principal plane, this tau theta shear stress is 0. Therefore, we can find, equate with 0, tau theta is equal to 0 is equal to sigma x minus sigma y by 2 sin 2 theta minus tau xy cos 2 theta, cos 2 theta. Therefore, we can say that sigma x minus sigma y by 2 sin 2 theta is equal to tau xy cos 2 theta. From this, sin 2 theta divided by cos 2 theta is equal to, can I say, 2 tau xy divided by sigma x minus sigma y. Therefore, sin theta divided by cos theta is tan theta. Therefore, this becomes tan 2 theta is equal to 2 tau xy divided by sigma x minus sigma y. Again, this is important formula. Again, this is important formula. Now, simplify this formula. Therefore, 2 theta is equal to tan inverse of 2 tau xy divided by sigma x minus sigma y. Again, therefore, theta is equal to 1 by 2 tan inverse of 2 tau xy divided by sigma x minus sigma y. This is the theta, and this theta is nothing but angle of any one principal plane with respect to vertical in anti-clockwise direction. This is important. This theta is angle of any one principal plane with respect to vertical in anti-clockwise direction. That means this theta can be a angle of major principal plane or can be a angle of minor principal plane. That we have to check as per loading in the numerical. But most of the time this theta comes as an angle of major principal plane. What I am saying, most of the time this theta comes as an angle of major principal plane, but not all the time. Sometimes it may be an angle of minor principal plane also. And if I add 90 degree in this theta, that is theta plus 90 degree, this is the angle of another principal plane. Angle of another principal plane. Jo, whatever may be the remaining principal plane, for this principal plane, this theta plus 90 degree will be the angle of another remaining principal plane with respect to vertical in anti-clockwise direction. With respect to vertical plane in anti-clockwise direction, this is again important. Right. Now we have to see maximum shear stress. We have to see for maximum shear stress. Now see, if I see what is the formula for shear stress on inclined plane, tau theta is equal to sigma x minus sigma y by 2 sin 2 theta minus tau xy cos 2 theta. And if I maximize this tau theta formula as per mathematics, or if we draw more circle, later we are going to draw more circle and there we will derive this formula. And according to more circle also, as per mathematics also, if I maximize this formula, I will get maximum shear stress as under root of sigma x minus sigma y by 2 whole square plus tau xy square. This formula we will get. Right. Now for 2D loading, again for 2D loading, there will be two tau max planes. For 2D loading, there will be two tau max planes in the material. On both tau max planes, tau max is acting. On both tau max plane, maximum shear stress is acting. The plane on which maximum shear stress is acting, the plane on which tau max maximum shear stress is acting is called tau max plane. Now again for 2D loading, there are two tau max planes separated by 90 degree angle. That means first tau max plane and second tau max plane. These two planes are separated by angle 90 degree. This is important, right? They are separated by 90 degree angle. Now on both tau max plane, on these both tau max plane, normal stress is also acting. And the magnitude of this normal stress is sigma dash is equal to sigma x plus sigma y by 2. On both tau max plane, the normal stress of magnitude sigma x plus sigma y by 2 is also acting. But on principal plane, uh, in previous in a few minutes back we have seen principal planes. On principal plane only principal stress is acting. On principal plane shear stress was zero, shear stress is zero. But on tau max plane, along with maximum shear stress, along with tau max, normal stress of magnitude sigma x plus sigma y by 2 is also acting. And very interestingly, the angle between any one principal plane, very important point, angle between any one principal plane and the nearest tau max plane is always 45 degree. Angle between any one principal plane and nearest, what I am saying, and nearest tau max plane is always 45 degree, is always 45 degree. In previous lectures, in some numericals, that is we have taken special cases, that is 1D loading and pure shear. In both special cases, see the end results, we have proved this, that is angle between any one principal plane and the nearest plane is always 45 degree. That means if the plane is, let us say this is a tau max plane, let us say this is a tau max plane, and on this plane the parallel stress acting on this plane is maximum shear stress, and the normal stress acting on this plane is sigma dash, that is normal stress acting on tau max plane, that is sigma x plus sigma y by 2, right? And for 2D loading, again there is one more tau max plane, separated at 90-degree angle, and again on this plane the parallel stress is tau max. On this plane also the parallel stress is tau max, and the normal stress is sigma dash, right? And the angle between any principal plane and the nearest tau max plane is always 90 any principal plane and nearest tau max plane is always 45 degree. Now from this we can come to the conclusion, that we can come to the important conclusions, that let us say for this type of loading, for such type of loading, 2D loading, let us say this is sigma x, sigma y, sigma y, right? This is sigma y and sigma y, and there is shear stress also, tau xy, tau xy and tau xy. For such type of loading, let us say if I calculate one plane, if I check one plane at angle theta, and let us say this plane is major principal plane, let us say this is major principal plane, right? Now how the planes we can represent in 2D loading? Now let us say this is a component, here I am representing the same component we are considering. Now at angle theta there is, we will get major principal plane. At this angle theta we are getting major principal plane, means normal stress on this plane, normal stress perpendicular to this plane is sigma 1, major principal stress, and shear stress on this plane is 0, shear stress on this plane is 0. And at angle 90 degree to this plane, at angle 90 degree to this plane, means this is the plane, they are at 90 degree angle, this is, they will be minor principal plane, this is will be minor principal plane. And on this plane the normal stress acting is minor principal stress, the normal stress that is perpendicular to the plane is minor principal stress, and shear stress on this plane also 0, also 0. Now angle between any principal plane and nearest tau max plane is 45 degree, means if I see major principal plane, from this major principal plane at 45 degree there will be first tau max plane, there will be first tau max plane. And on this tau max plane, the maximum shear stress is acting, means parallel stress is tau max, and also there is normal stress acting on this tau max plane, and the normal stress acting on this tau max plane is sigma dash, which is equal to sigma x plus sigma y by 2. Again the angle between principal plane and nearest tau max plane is 45 degree, means angle between minor principal plane and first tau max plane is also 45 degree. And there is one more tau max plane which is perpendicular to first tau max plane, therefore there will be one more tau max plane, this is second tau max plane, second tau max plane, which is perpendicular to first tau max plane, that means it is at angle 45 degree from minor principal plane. at angle 45 degree from minor principal plane. And on this tau max plane, the normal stress is sigma dash, that is sigma x plus sigma y by 2, and the shear stress is tau max. Shear stress is tau max. This is how there are different planes in 2D loading. And interestingly, there is one very special note. There is one, or there are two special notes. That is note number one. Note number one: on mutually perpendicular planes, the magnitude of shear stress is same. On mutually perpendicular planes, the magnitude of shear stress, what I am saying, magnitude of shear stress is same. That means if I calculate shear stress on any plane theta at angle theta, and if I see magnitude, means we have to take positive value, then the same magnitude will come on theta plus 90 degree plane. Here also we can see, if I calculate shear stress on 45 degree plane, then you will find same magnitude on 135 degree. On 135 degree magnitude I am saying, it may be a negative. On, let us say, on some plane, on theta plane, shear stress is 10 MPa. Then on theta plus 90 degree, the shear stress, it may be minus 10 MPa, but the magnitude is same. Magnitude means we have to consider positive value. It may be a negative, but we have to consider positive value. Again, if I calculate shear stress on 10 degree plane, then we will find the same shear stress magnitude on 100 degree plane also. Right, this is the first note. That is, on mutually perpendicular planes, the same magnitude of shear stress is acting. And second note is also important. The sum of normal stresses on any two mutually perpendicular plane is same. Sum of normal stresses on any two mutually perpendicular planes, mutually perpendicular planes is same. This is also very special and very important note. That means the meaning of this note is, the sum of normal stresses on any two mutually perpendicular planes is always same. That means if I find sigma theta plus 90 degree, the sum of normal stresses on mutually perpendicular plane, then I will find same value on sigma x plus sigma y. Sigma x and sigma y are perpendicular to each other or not? Again, I will find same value on sigma 1 plus sigma 2. Right, that is minor principal plane and major principal plane. Again, I will find same value on sigma dash plus sigma dash, that is normal stress on both tau max plane. Sigma dash is a normal stress on tau max plane, and there are two tau max plane which are separated by 90 degree. Therefore, I will find same value on sigma dash plus sigma dash. Again, it is also equal to, if I find normal stress on 10 degree plane and add this on 100 degree plane, right, means the sum of normal stresses on any two mutually perpendicular planes is always same. That means while calculating normal stress on, acting on tau max plane, that is sigma dash, we can do two ways. We can calculate it by two ways. Here I am erasing. Now the normal stress sigma dash on tau max plane we can calculate by two ways. That is, this sigma dash is equal to sigma x plus sigma y by 2, or we can say sigma 1 plus sigma 2 by 2 also. Right, now come back to the initial formula. What are the principal stresses? That is sigma 1 comma 2 is equal to, formula is sigma x plus sigma y by 2 plus or minus under root of sigma x minus sigma y by 2 whole square plus tau xy square. Therefore, sigma 1 comma 2, I can write sigma x plus sigma y by 2 is sigma dash, normal stress acting on tau max plane, plus or minus under root of sigma x minus sigma y by 2 whole square plus tau xy square. This is tau max. Right, this is how we can write the formula of principal stresses. Now all these formulas and all the statements that I have made regarding principal planes and maximum shear stress plane are very much important for any competitive exam. Not for only GATE, for any competitive exam, all the statements are very much important. And all the conclusions as well as all the formulas we will derive graphically in more circle. Right, now as of now, remember everything. Thank you dear students. In next lecture we will take one very good quality numerical on these principal stresses concept.